Welcome, cadets, to Lesson 31 on atomic spectroscopy. I hope everyone is doing great. It is the 27th of April, and this Wednesday is GR3, Lesson 32. Just a quick reminder, it will cover material from Chapter 11 and 13 through 16 in the 8th edition Harris textbook, so that should be EDTA titrations and electrochemical methods, redox reactions, redox titrations, etc. It will also cover material from experiments 5 and 6, the EDTA titration and determination of calcium carbonate content, and potentiometric titration of iron. So be prepared to work similar calculations and understand the theory of the chemistry happening in those experiments. Quick reminder, your sapling homework is also due on Wednesday, and that is according to the 9th edition chapters, which is 12 and 14 through 17. Today we're going to cover atomic spectroscopy, which is chapter 20 in the Harris textbook. So we will look at the different methods involving absorption and emission of light. So we have different acronyms for the techniques based upon either the absorption or the emission of light. And we need to get our analyte species up into the gaseous phase. So what we call the ground state atomic gaseous phase, and we're going to measure either the absorption or emission of light. And the manner in which we get that species into the gaseous phase is going to require a lot of energy, heat. So our different techniques use different strategies for doing that. So we have flame methods, we have electrothermal methods, and we have plasma methods. So we will look briefly at the theory, instrumentation, and applications for each. The basic operating theory of atomic spectroscopy involves either the absorption or emission of light in the typically visible spectrum that comes from excitation of electrons within the atomic orbitals. So outside of the core orbitals that are filled, we have valence electrons in different atomic orbitals. For example, sodium is element number 11 with 11 electrons and protons. And so those 11 electrons, this is the electron configuration for the sodium atom. The s orbital is filled, the 1s orbital is filled, the 2s orbital is filled, the 2p orbital is filled, and outside of the noble gas core, we have one electron in a 3s atomic orbital. So here sits down here the energy of the electron in the 3s atomic orbital. That is the ground state configuration. But if we hit the sodium atom with light of the correct wavelength, such as that at 589 nanometers, we excite that electron to a higher energy orbital, such as a p orbital, and so we get the absorption of radiation at that particular wavelength. So this is what's known as the characteristic line spectra of sodium, and so you will see these very narrow absorption bands at these different wavelengths due to the excitation of that one electron up into other orbitals. You will notice that the magnitude of the absorbance, for instance, the 3s to the 4p, okay, exciting this way, the magnitude of the absorbance is small compared to that of the 3s 3p transition, much bigger. And that has to do with the statistical probability of that excitation happening. But the point is, we can identify sodium as an element in a sample if indeed we observe that that species, when presented in the ground atomic state, absorbs light at 589 nanometers. I would like to start by doing a comparison of the different atomic spectroscopic methods, instrumental methods, how they compare to each other in terms of figures of merit, and also versus the electrochemical methods that we just covered. All of these techniques have the capability of giving us information about what particular element is present and at what concentration in the sample. So we call these our elemental methods of analysis. So to begin, the different techniques that exist, we have methods in which we get our analyte species up into the gaseous phase using a flame, or we can use an electrothermal furnace, or we can use a plasma. Okay, and then in addition to traditional plasma, we also have plasma methods in which we interface a very specific detector. We're going to use a mass spectrometer as our detector. So those are the different methods that exist. And so if you compare limits of detection, okay, you're going to see that moving left to right, we are increasing the capability of that technique to detect lower and lower and lower concentrations. And so the plasma methods in which we interface with a mass spectrometer, and just FYI, we call this ICP, inductively coupled plasma mass spectrometry, going to give us the best detection limits, although some of our furnace methods can rival as well. The linear range, here's the comparison, okay, precision, okay, all pretty good. There's really not one that's hugely advantageous there. Interferences, so one thing we need to be careful of when we're analyzing for different elements is, does one element interfere with the other? So we call that a spectral interference. If we don't get all of our species up into the gaseous phase, we can have chemical interferences if they're still molecular in nature, so on and so forth. So as you see, the simpler techniques can have some interferences, whereas mass spectrometry does not. Sample throughput. So this is a practical consideration of, if you're a laboratory that is, makes its money by analyzing a lot of samples in a day and you charge on a per sample basis, you want a high sample throughput. So some instruments come with what we call auto samplers, where you can load up a tray with 100 samples and it will sequentially analyze one right after another. So that's an important thing. So in terms of throughput, you can see comparatively the flame methods pretty good. Furnace methods not so hot. And then the plasma methods have a huge advantage because we're analyzing all elements at the same time as opposed to one per analysis. So those are super fast on throughput. Then we look at the nature of how we present the sample for analysis, and you can look at that data. And then finally, other practical considerations. How much sample do you have? Sometimes you're very limited. If you're a forensic scientist and you only have what was collected at the crime scene and it's a tiny amount, that could be a consideration. And so the method that has the huge advantage on sample volume are the electrothermal methods. They require just a few microliters of sample. And finally, the cost of the method, always a practical consideration. So our flame methods are the least expensive, followed by the furnace methods. Then when we get into plasmas, those are expensive. We consume argon and we need a more specialized detector. And an ICP mass spectrometer is very expensive. You're talking $120K versus you can get a really good atomic absorption flame instrument for $20K or less. And one final note, we did just cover the electrochemical methods, which do give us information about different species in different oxidation states. So, you know, they are very inexpensive compared to all of these methods. You can purchase electrochemical devices typically for a few thousand at most. But the big limitation is throughput. We typically can only analyze one sample at a time. And the limits of detection actually can be very competitive if we're doing stripping voltammetry. So they do compete on that level. Their sample volume is medium. We usually need a few milliliters at least. And the big advantage to the electrochemical methods is they are selective for oxidation state. I can distinguish iron 2 from iron 3. And once again, their cost is a lot less expensive than the spectroscopic methods. So there's the big view of the elemental methods of analysis and how they compare from a performance perspective. To further illustrate how these methods compare with respect to the figure of merit known as the limit of detection, so remember that's the least amount of analyte species that gives a signal that's at least 3 times the standard deviation of the blank sample. It kind of depends on the element we're analyzing. So you can see we have our flame atomic absorption method here, electrothermal here, atomic emission method with flame, and then we get into the plasma methods, okay, ICP atomic emission spectroscopy, and the final one is flame atomic fluorescence spectroscopy. So if we look at each element, you can see that it just kind of depends. Our plasma methods tend to give us, for instance, calcium. Plasma methods are going to tend to give us much lower detection limits, but it's not necessarily true for all species. If you look at, for instance, magnesium, you can see that our electrothermal methods are very competitive and give us really low detection limits. So in consideration of that very important parameter, if we're doing trace analysis where the elemental species is present at very low concentrations, you kind of want to give consideration to each element and each method if you have the option of choosing. Now we want to focus our attention to the atomic spectroscopic methods in which we get our analyte species up into the gaseous ground state form using a flame. So we're literally going to introduce our solution into a flame with an oxidant gas and a fuel gas that combusts. And so what we're doing, if we have an absorption method, my species ends up in the ground gaseous phase, atomic phase. Okay, each element absorbs characteristic photons at specific wavelengths. And so I excite my element up into some excited state. So my absorption techniques, I am measuring the intensity of the light that gets absorbed from that characteristic wavelength. Okay, so that's your absorption techniques. Emission is where this species, once in the excited state, after some time settles back down to the ground state. And that is going to emit that characteristic photon. So this is your emission method, and this is your absorption method. Okay, so how that might look. So for atomic emission, we're going to suck our solution up into a flame, and the heat from the flame is going to eventually get it up into the gaseous phase as a free atom. Okay, and so we are going to use the heat from the flame to get that electron up into the excited state, and at some point light is emitted we use a wavelength selection device and detect it. So atomic emission spectroscopy, our acronym is AES, that's how that works. Okay, atomic absorption spectroscopy, this is our absorption technique. So we're going to suck our solution up. It eventually will be presented to the flame up here in the ground vapor state, atomic vapor state, and we're going to measure the absorption of light. We're going to use what's known as a hollow cathode lamp, which is going to give us that characteristic wavelength for that element. And I'm going to measure the intensity absorbed by my atoms. Obviously, you're going to need a wavelength selection device, a monochromator, and a detector. Fluorescence methods are similar. The only thing that's slightly different, so schematically down here, the energy diagram. So we're going to excite with a characteristic wavelength for that element. Okay, your characteristic wavelength, excitation. And now a little bit of that energy gets converted to heat and is given off in the form of heat. That's what we call a non-radiative process. And so when it comes time to drop back down to the ground state and emit a photon, okay, that emitted photon is at a longer wavelength than the excitation because some of that energy was given off in the form of heat. So when that happens, that's the distinction of fluorescence versus emission. This slide is going to help you understand the process of getting our species of interest up into the ground atomic vapor state. The process is called atomization. Okay, so consider that you have some analyte species of interest down in a solution. Okay, it could be bound or bonded to some other species and it's in solution. Okay, so to use these techniques, I have got to get this element, A, up into the form in which it's an atom, a free atom, in the gaseous phase, and it's the ground state gaseous phase. So what has to happen along the way? Well, first of all, I must nebulize, so that's the process of aspirating or drawing that solution up, okay, into a capillary tube. Okay, if in that process it contacts an object, there's different ways of doing this, but I can get it into an aerosol where my droplets are tiny. Okay, so we aspirate the sample up into a capillary tube, okay, and then we get it into little tiny droplets, okay. So if I'm going into a flame which has heat or some other source of heat, our electrothermal methods are going to use electrical heat, and our plasma methods are going to use a torch. We'll talk more about that later. But for our flame methods, we use a flame. Okay, so the first thing that we're going to do is we're going to evaporate, we're going to get rid of the solvent, the water, or whatever the solvent is. So this molecular substance is now going to be in the solid form, and I'm going to lose, let's say water was my solvent. So I'm losing the water, I'm losing the solvent. Okay, so at this point here, okay, I no longer have solvent, and the next step is to go from the solid phase to the gaseous phase. So I take my molecular species up into the gaseous phase. Once again, all of these steps require energy in the form of heat. Okay, so that's sublimation if I go directly from the solid phase to the gaseous phase. Okay, so now I have gaseous molecules. The next step, if I provide further energy, okay, is to break the chemical bond between those two species. If I break the bond, I should free the atoms. Okay, so at this stage, I now have atoms. And once again, this is going to require heat, energy, and a lot of it to break those bonds. Okay, it is undesirable to continue this process and ionize my species. That is not desirable because only this species, the ground vapor atomic state, is going to be able to absorb the characteristic wavelength that I wish to measure as an absorption, or at some point excite it and drop it back down to the ground state. So this is the process of atomization. And once again, it is the reason that we must either have a flame or a furnace or a plasma to get our analyte species of interest into this appropriate form. We're going to switch gears to the specific technique of atomic absorption spectroscopy. If we are doing atomic absorption, our source lamp has to be what we call a hollow cathode lamp. It is a line spectrum in which we only emit the characteristic wavelength of whatever element we're trying to analyze. Okay, so unlike our broadband sources, we're only going to emit a single wavelength. How it works, there is argon gas in the tube, the enclosed quartz tube. That argon gas, okay, we're going to apply an electrical potential across this anode, that's the positive terminal, and this cathode material, that's your negative terminal. Okay, so when we apply the potential here, we're going to ionize my argon. So I now have positively charged ions. These ions here, once formed, I'm going to put the positive charge on there, they are going to be attracted to the negative terminal and slam into the cathode. Okay, so if I'm wanting to analyze, for instance, for sodium, my sodium hollow cathode lamp would be comprised of sodium as my cathode material. When the argon ions slam into the cathode, those sodium atoms sputter off the surface in an excited state. At some point, my excited sodium atoms will settle back down to the ground state and in the process emit a characteristic photon of sodium. So now I focus the wavelength coming out of my hollow cathode lamp on my flame where my sodium atoms are sitting, ready to absorb that characteristic wavelength. The one thing you need to know about operating a hollow cathode lamp is you must choose the current at which you operate the lamp, the amperes, okay? And it's a trade-off with sensitivity in that if you operate at higher current, okay, you can increase the sensitivity. You'll get a more intense emission of light if you are operating at a higher intensity than a lower. The problem is as you operate a higher current, you get what we call Doppler broadening. So if this is my characteristic wavelength that I want to excite my atoms with, at a lower current, I get a nice distribution like this, in which the most intense wavelength is at my characteristic wavelength of my analyte species. If I operate the lamp at too high a current, we get this kind of pattern, where now I get emissions at different wavelengths that are not my characteristic wavelength, and that can cause some problems. So it's a kind of a trade-off that you have to play around with the operational current of your hollow cathode lamp. So if we're doing either atomic absorption, atomic emission, or atomic fluorescence, we are using a flame as our heat source to atomize our analyte species of interest. So the component of the instrument which gets our analyte species up into the ground vapor state is what we call a burner nebulizer system. We must nebulize, that is, we must draw up from our sample, usually in solution form. We must draw up our sample into this component of the instrument. Okay, so using the nebulizer, okay, and it's what's known as the Venturi effect. A pressure drop sucks the sample up. Okay, so our sample gets drawn up and it's coming in and it hits this glass bead. Okay, that causes it to form a mist, a bunch of little tiny droplets in which we have just small amounts of solvent. Okay, and so within the burner nebulizer system, we must combust a gas. So we have a fuel gas coming in here. Okay, so usually a hydrocarbon of some kind. Acetylene is a common fuel gas used, and then we must have an oxidant gas. So it can be simply air, or it can be oxygen, or it can be nitrous oxide. It can be a variety of oxidizing gases. Okay. All right, so we are going to have just a little hole that allows our tiniest of droplets to enter into here and get up into the flame. Okay, let me do that again in a different color so you can see that. The little tiny droplets get up into the flame, okay? And once again, that desolvation process happens. We get rid of the solvent. We sublime the sample, get it up into the gaseous phase. We break any bonds, and at this point, our species of interest, whatever it is, hopefully is presented in the ground vapor state. Okay, so that is the burner nebulizer system. And the one thing we have to be careful of, sometimes the burning velocity of our gases, if they don't move up here fast enough, we can get actually an explosion in the chamber. So you just need to be careful in picking your air and your oxidant and your fuel gases, and the flow rates that you operate those gases, and the burning velocity. So when we're doing our flame methods, either atomic absorption or atomic emission, these are the most common oxidant and fuel gases that are used. So the table to the left comes from your Harris textbook. So here's your common fuel gases. So as you'll see, acetylene is very common, hydrogen or cyanogen. and common oxidant gases, air, nitrous oxide, oxygen, etc. And the important thing to recognize is the temperature of these characteristic combustions. Okay, so the temperature of the flame is going to dictate our efficiency in getting our element species of interest up into the vapor state. Sometimes if our species like calcium, if it's complex, if it's an oxide, sometimes it's going to take a higher temperature to free up those calcium atoms. So just know that the flame temperature depends on the nature of our sample and how hot we need the flame to be to get our species up into the correct ground atomic state. So that's why we have to choose different mixtures of our fuel and oxidant gases. This is from the Skoog textbook, the instrumental analysis textbook. So here's the temperature of your different gas combinations. And here's the last thing that I was talking about with the burner nebulizer system. You also have to pay attention to the burning velocity of those combinations of gases. So you'll notice that some of these that gets us to the hotter temperatures, such as acetylene oxygen, actually has a very fast burning velocity. So we want to avoid explosions in our chamber. So you just need to make sure your flow rates are such that you don't risk this happening. So these instruments come with a lot of safeguards that pretty much don't allow you to have settings in which this is a possibility. So this is just one of the advances made in instrumentation over the years. When doing atomic absorption spectroscopy, we just need to be aware that we have to align our source lamp so that it is focused at the right part of the flame. So our hollow cathode lamp is out here, and it's emitting our characteristic wavelength for a particular element. Okay, so where do we want that source radiation to hit our flame? Where is my analyte species likely present at the greatest concentration in the ground vapor state? So it turns out that in a flame, you have different zones. So you have this primary combustion zone down here, okay? And then you have what's known as the interconal region, which is this part of the big part of the flame here. And then there's this secondary combustion zone up here. Okay, so where we want our source radiation to be focused is in this interconal region. That's where our analyte species of interest, A, is present in the greatest population in the ground vapor state. So that's a feature that you have to choose when setting up your instrument. You have to align your source lamp and where it's going to focus the radiation relative to the flame. The design of atomic absorption spectroscopic instruments can take on different block diagrams, different features. One thing that's common is when we look at our flame, okay, sometimes if we have more than one element present, obviously, you're going to get emission of characteristic wavelengths from element number 1 and element number 2, so on and so forth. Okay, and there can be some fluctuations in the temperature of the flame, which affects the intensity of the light coming out of different wavelengths, etc. And so one thing that we want to be careful of is, since there's a lot of emissions happening, we want to make sure that the only light that we're actually going to detect and measure is that coming from my characteristic element. So here's my analyte species of interest. I excite it with the right wavelength. And so the only light I want measured is the light absorbed at this characteristic wavelength. So some of these other emissions are going to result in light coming off in different directions, etc. So one thing that we want to do is with our detector, this is our detector. Okay, we just want to make sure it's only going to respond to wavelengths of light that came from our source lamp. So one way of doing that is we can modulate our power source. So superimpose a frequency onto our power source so that the characteristic wavelength is only coming through at certain periods of time, and then we can tune our detector to this frequency that the source lamp is operating at. So if any light bounces around our instrument and comes from other sources, we will not be detecting those. Okay. The other way of getting around this is to either use a, like I say, a modulated power source where it's on for a certain period and off, and that's the frequency of modulation. Or the other thing we can do is use a chopper in our block diagram. So there's your source lamp, and so half the light's going to go through the flame in your analyte species of interest, the other half doesn't. It diverts, bounces off these mirrors, and recombines. So that's going to provide the background correction. Go through our monochromator, in which we select our characteristic wavelength for detection, amplify it, and read out. So once again, the design of most atomic absorption instruments includes either a modulated power source or a chopper to help get rid of background radiation. Alternative to our flame methods in atomic spectroscopy, either absorption or emission, we can use as the energy source to excite our analyte species and get it up into the ground vapor state. We can use a furnace or an electrothermal source. Okay. These can be made of different materials, so it can be a horizontal graphite tube or a carbon rod or a tantalum ribbon. So basically, the huge advantage with using this as our heat source, we introduce very tiny droplets of our sample onto the graphite tube. Okay, there's a little hole here, so you would use a syringe of some kind to draw up just a few microliters of your sample. Put that little tiny droplet in there, okay, through electrical resistance heating, okay. We are going to be able to achieve very high temperatures, much hotter than that in which we can accomplish in a flame. So that provides more efficient atomization of our analyte species of interest, getting it up into the ground atomic vapor state. Okay, so the more efficiently we do this, So once again, if you have oxides in which it's going to take a really high temperature to free your element from the oxygen, okay, this gets done more efficiently this way. So what this does is it lowers your detection limits because it presents a higher concentration of your analyte species in the correct form to absorb the radiation. So as we noticed, our electrothermal methods for many elements provide some of the lowest limits of detection. So the huge advantages: you only need a tiny amount of sample. It provides very efficient atomization because of the high temperatures that it reaches, and therefore it provides the lowest detection limits for many elements. In a similar fashion, we can use a technique known as glow discharge in order to analyze solid samples. You just put your solid sample here, and once again, applying a huge electrical potential across two electrodes generates a lot of energy that then gets the solid sample up into the gaseous phase, and it frees each element out and presents it in the ground vapor state. So these collective methods can be very useful for direct analysis of small samples, whether they be in solution or liquid form or solid. Switching to one application issue, if we're doing atomic absorption spectroscopy, either using flame or furnace, there is the potential for ionization interferences. What is that? All right, so if M over here is my analyte species of interest, if my flame is too hot, okay, some of my analyte species of interest might ionize. That's bad because this species will not absorb the characteristic wavelength and will not be detected. So to get around this effect, okay, down in this table, you will see the ionization potentials of different elements. Obviously, some elements ionize more efficiently than others. If I intentionally add to my solution an element that is easily ionized, such as potassium, this process will occur efficiently. If that occurs efficiently, all of a sudden there is an excess amount of electrons in my flame. If there's an excess amount of electrons in my flame, that's going to drive this equilibrium back this direction, converting my ionized species of interest back to its ground atomic vapor state. So now it is in a form capable of absorbing that characteristic wavelength and being measured. So looking at the data at the lower right here, we're analyzing the element strontium. First, in the lower two frames, calibration curves, we are using, sorry, let me go back. In the lower two plots of calibration curves, we're using an acetylene flame, so that's a lower temperature flame. And you can see in the upper plot, into which we've added no potassium, okay, it's linear and then it starts going up. We have a positive deviation. That's a sign that you have an ionization effect going on. Okay. Alternatively, if I had taken my solution and added potassium at 1,000 micrograms per mil, okay, once again, those excess electrons pushes my strontium back to its ground vapor state, and I get rid of that positive deviation in my calibration curve. Alternatively, if I go to a different combination of gases that gives me a hotter flame, I can make my method more sensitive, and I can correct for any ionization interferences by adding concentrations of the potassium to higher levels. So in doing that, I can push the sensitivity of my method to a higher level, okay, while minimizing the ionization effect. Another consideration in application of our atomic absorption or emission methods in which we're using a flame or a furnace, we sometimes have to account for the fact that, our samples are complex, and if we have something in our sample such as a species like calcium hydroxide, okay, if we don't efficiently break that species up into its characteristic elements, it's going to give rise to an absorption, a broadband absorption. Okay, so if I have my analyte species of interest, let's say we're doing sodium, and I get it up into the ground atomic vapor state, okay, and I hit it with the characteristic wavelength of sodium using a sodium hollow cathode lamp, okay. This absorption right here is the absorption of this is my characteristic wavelength of sodium right here. But you will notice that if I have some interfering species in the flame that give rise to broadband absorbances in the visible spectrum, you can have this background absorption going on. Okay, so how do you get around that? Well, one thing you could do is remove any interfering species from the solution before you analyze it. That can be cumbersome. It can take quite a bit of time to remove those species. The other thing you could do is correct for that background absorption. So how does one do that? Well, in our instrument, in addition to our hollow cathode lamp, which is, if I'm analyzing for sodium, that's a sodium lamp, I'm going to use a deuterium lamp. Okay, if you remember, this is a broadband source lamp that's going to emit wavelengths across a broad spectrum, okay, many different wavelengths in the visible spectrum. Okay, so what that allows me to do is if I have both of those source lamps and I alternate with a chopper, little segments of the light coming from the hollow cathode lamp, the deuterium, hollow cathode, deuterium, etc. Let that light pass through my sample, in this case introduced using my electrothermal method. What I want to do is I want to measure the background at 2 wavelengths on either side of my characteristic wavelength. So this is wavelength 1 and wavelength 2. Okay, so if I just draw a straight line across those two, okay, then I can estimate the absorption happening at my characteristic wavelength from the interfering species separate from the absorption coming from my analyte species of interest. So using a deuterium lamp, I can make the measurements on either side of my characteristic wavelength, and then I can subtract that background contribution to the absorption coming from my element of interest. Another potential interference is overlapping characteristic wavelengths from the different elements. This is very uncommon because they are so narrow. The absorption bands in line spectra are so narrow, it's very uncommon to have two elements that overlap. That is, they give rise to an absorption at the exact same wavelength. Okay, but in the event that it does happen, we can use a magnet to separate out the absorption from one species versus another. And so this is the design of an instrument in which we introduce the magnet to separate out these two characteristic wavelengths. This is called the Zeeman effect. And once again, this is how we deal with interferences involving the overlap of the characteristic wavelengths of different elements. And the final group of techniques are our plasma methods, in which we don't use a flame, we don't use a furnace to atomize our samples. We use a plasma, a torch, an argon torch. How this works is argon gas is introduced into the torch. It is combusted so that it ionizes. And then we subject these ions to coils into which we run a current. Okay, so depending on the current that is applied, we get our argon ions moving in one direction and slamming into whatever's in its way. And then we reverse the current. So the current goes in one direction and then we reverse it. When we reverse it, the argon ions, instead of moving in this direction, abruptly move in the opposite direction. And they slam into each other. And when they slam into each other, a lot of energy is generated. That energy in the form of heat. Okay, so the huge advantage to plasma methods is we are going to get upwards of 10,000 degrees. Okay, much hotter than either a flame or a furnace. The higher temperature allows for a much more efficient atomization of our samples. And that's going to translate into much lower detection limits. So we can get a very low concentration of our species up into that ground vapor state capable of absorbing or emitting radiation. In this case, these are emission techniques. So we do take our analyte species of interest. We are going to get it into the ground vapor state, and at these high temperatures, it's going to be excited. And after some period of time, it settles back down to the ground state, emitting the characteristic wavelength of that element. Okay, so the group of techniques, there's a couple. We can use the argon torch, the plasma, and this is called an inductively coupled plasma, so ICP. Okay, atomic emission spectroscopy, okay, is one in which we just use as a detector. Okay, we are going to detect these characteristic wavelengths from a bunch of different elements. So element number 1, element number 2, element number 3. We detect the emission from a bunch of different elements all at the same time. So this is very powerful in terms of an analysis time standpoint. We get information on all elements with one analysis. So in addition to the huge advantage of efficient atomization, we're at these higher temperatures, so we have lower detection limits. We also have the huge advantage of what we call simultaneous multi-element analysis. Okay, you aspirate your sample up into this torch, and you're going to get information not only about sodium, but anything else that's in the sample. Okay, so if the nature of our detector are photodiode array kind of charge coupled devices, then those instruments are ICP atomic emission spectroscopy instruments. They cost a lot more. The torch costs more than a flame burner nebulizer system or electrothermal system. The cost comes from a couple of aspects. The instrumentation is more expensive, but we are also combusting argon gas, and that is a consumable that is very expensive. The other alternative to the detection is, instead of using a charge coupled device to measure all those wavelengths, we can actually interface our plasma. So here's our plasma and everything coming out of it. Pass that into a mass spectrometer. Okay, that is an instrument that can analyze any species on the basis of mass. Extremely powerful in being able to detect anything that's in that sample. So this slide just gives you a comparison for analysis of nickel by the different plasma methods. So the top one is ICP atomic emission spectroscopy, in which the nebulizer system is what we call a pneumatic system. And at that point, our limits of detection in terms of milligram per gram, 3 to 50. If we have an ultrasonic nebulizer, it's just a more sophisticated way of and more efficient atomization. We have lower detection limits. Graphite furnace, once again, don't ever underestimate the capacity for graphite furnace to have low detection limits. For nickel, much better. And the best is ICP mass spectrometry, in which we get down to much lower detection limits. The last slide I wanted to show you is the sophistication of the interface between the plasma torch and the mass spectrometer. These kinds of sophisticated instruments take years and years and years of research and development to get them to operate. Once again, this technique has by far and away the lowest detection limits, and we get information about all of our elements present at one time. These instruments are in the ballpark of 120K and can be more expensive than that. But it's not a simple system. Your torch and the plasma is here. Okay. Years of research, they had to learn how to get the emitted species to be transferred into the interface. So the components here, this is the interface where we're going to select one ion at a time to enter into the mass spectrometer, which is the part over here. We'll talk more about the design of those instruments when we get to that chapter in the book. A mass spectrometer is going to analyze on the basis of the mass to charge ratio of the different ions entering here. And we will detect over a fairly short period of time the concentrations of a whole variety of species. It's a very powerful instrument. So in summary, huge advantages to ICP mass spec. It's a plasma emission method, so no hollow cathode lamps. We don't need the source lamp. We can analyze multiple elements at the same time, get data quick, and it provides the lowest detection limits. Huge disadvantages: it's a very sophisticated instrument. The cost is prohibitive, and they're not easy to calibrate and infer the data. So the level of expertise of the operator is quite sophisticated. And the other additional consideration is the cost of the consumables. The argon gas, which depending on how many samples you run in a given week, this can be hundreds or even thousands of dollars. So this ends our consideration of the atomic methods of analysis. I hope you enjoyed it and have a good day.